So let's do section 2.4 linear functions. So I just give you some basic information. The good thing for most of you is almost all of this should be review. We're going to do a few extra things, but most of it will be review. So function f is a linear function if for some constants m and b we have f of x equals m of x, mx plus b. So that's f of x is equal to mx plus b. So I'll give you a specific example. F of x is equal to 1/2 x minus 20. In this case, my m is 1/2, and my b is equal to minus 20. Notice that my m and my b are constants. They don't vary. This is a variable in x. Here are two other things I want to point out. Function notation, we often use f of x. F of x is equal to some mathematical expression with the variable x. In this case, x is the input variable, and it's the exact same x that we see when we actually have a graph. It's the same x that the axis denotes, and this is usually considered the y-axis, but here is the equality. When we're talking about functions, you can either relabel the y-axis or f of x, but always remember this, that f of x is equal to y. That's going to be helpful for you. I'm thinking. I know it was for me when I was looking at these things. The other thing I want to talk about functions really fast is f of x. The letter f just names the function. In parentheses, you have your input variable, and the input variable is always going to come from whatever the horizontal axis is named. Normally the horizontal axis is named x, but later on, or maybe already, I teach so many classes I can't remember, you might actually have something f of t, where t stands for time, and in that case they just simply rename x with the variable t. The point is, it's the input variable, and when plotting it, it's going to correspond to a point here. And if this is a function, let me just draw a linear function. So that's a linear function. That's a line, it goes straight on. I'm not going to give it, I'm just going to talk about it in the abstract. That's f of x is equal to mx plus b, and I want to look at a particular point on the function. So I'll look at this point right here. So if we go down, straight down, I'm almost there, that denotes the x value, and over here I find the y value. So remember, this is a point. So a point always has two coordinates. This has a coordinate x, comma, y. That x stands for this x down here. For example, it could be 5. And this y stands for this number over here. For example, it might be 10. But what I want to talk about is the notation. Every point that lies on this line is an ordered pair. But here, I don't have y anywhere in my function notation. That's where this comes in handy. Y, the value of y, is equal to mx plus b. So you literally, if you wanted to, you could write a pair, an ordered pair on the line as x, f of x. The second thing I want to remind you of is that f is just the name of a function, x is the input variable. We could just as well name that function g. You always have to specify an input variable. Sometimes when we know the input variable is x, we'll just refer to it as the letter f or the letter g. It could be p of x, capital S of t, if our input variable is t. All of these just name a particular function. There's nothing really special about f, but f is kind of our default, probably because it stands for function. Or I guess it has the same first letter as the word function does. So let's move on. So here is an important change. If you downloaded these notes, there was a typo in my notes. Before I said if m is not equal to 0, then the domain of f is minus infinity to infinity. And then oddly enough, down here I start talking about the range. Well, I meant to say the range in both places. I just noticed that, made the change, uploaded it. So if you're following along and you say in your notes say range right, if your notes say domain right there, scratch them out and put in range. So this is a theorem, it's a fact. If m is not equal to 0, and that's our function, f of x is equal to mx plus b, then the range of x, that's all of the values that the y coordinate takes, is minus infinity to infinity. And here's an interesting challenge for you. Is it also true that as long as m is not equal to 0, that the range of f is minus infinity to infinity? So how do you go about answering this question? Here is really all you need. Look up range. So you know what the range of a function is, if you don't remember. And then look at the obvious. Consider the case when m is equal to 0. Really, that's all you have to do. Because literally, I have taken care of every case of every possible number. I've taken care of every last one of them except 0. So consider the case when m is equal to 0. I'll just leave it at that. So let's actually graph a linear function using intercepts. So let's go about doing that. I want to have a program up. So let me get my deep in screenshot. Because I'm going to use this little bit of graph right there. I grabbed the wrong one. That's not the one I like. I have too many screenshot programs. FlameShot is the one I want. And you'll see why. It gives me the option of saving it to the clipboard. You say, well, if you're wondering where those programs are on Windows or on Mac, these are all Linux-based programs. So they may have a Windows version, I don't know. I actually don't care at this point anything about Windows. Here we go. So here we have what we're supposed to do. So we're going to graph f of x is equal to minus 2x plus 4 using the intercepts. So here's just a little bit of review. The point on the graph of a function with x coordinate equal to 0 is the y-intercept, and the point with the y slot or y coordinate equal to 0 is the X-intercept. And I have to add one last piece to this recipe to make it a true, mathematically true statement. Provided, what do I have to provided? Provided they exist. There are graphs of lines that don't have x-intercepts, and there's graphs of lines that don't have y-intercepts. So here is the procedure. I'm just going to give you the procedure, and it's really simple. So the first thing you might want to do, until you get used to this, you've got two options. You can find the, let's go back over here. You can find the y-intercept by plugging in, it's terrible writing, a function with x-coordinate equal to 0 is the y-intercept. So you can find the y-intercept by evaluating, am I dark enough? F of 0, because that's the input value. And that's minus 2 times 0 plus 6, and that's equal to 6. So that tells me the point 0, f of 0, which is equal to 0, 6, is my y-intercept. So that's going to be, that's 1, 2, 3, it's going to be right here. We're going to find this right there. You also might recognize this is in a special form, and you may be able to look at the value right there of 6 and know immediately that the value of the y-axis for the y-intercept point is 6. Here's another easy way for you to find the intercepts. Graphing tables of values. This will be the x, and this will be the y. And for the intercepts, this will always work. But notice we require 2 points to create a unique line. And it may be that we can't use the intercepts to do that. This assumes that the intercepts are 2 different points. If the x-intercept and the y-intercept are the same point, then that point must be the origin. Now I'll give you a clue right here. If you have f of x is equal to mx plus b, and b is not 0, that means it appears in the equation, then the x-intercept and the y-intercept are different. And remember, you can always write this as y is equal to mx plus b. You should be able to immediately see that those two are the same. So what I do for my classes is I say just do kitty corner zeros, because you're looking for the intercepts, and this will always tell you what the intercepts are. It will tell you if they're distinct, and if they are distinct, then you've got 2 different points. And we already discovered when x is equal to 0 that the answer to y, because remember y is equal to f of x, is equal to 6. So remember, this is 0, this is x, y. Every point is x, y. So now what I want to do, I have to plug in y. So my f of x itself is 0, which is the same thing as saying y is equal to 0, and I solve for x. Minus 2x plus 6. I take the 6 over, and it becomes minus 6. And then I divide both sides by minus 2. And I get 3 is equal to x. So I'm going to come down here and point at 1, 2, and plot it. on the graph, and then all we do is just draw our line through those 2 points right here and right here, going up that way, and that's pretty much the graph. So you all should be able to take care of that fast. The only difference here is we're starting out with function notation, but sorry, that's a program I'm working on. There we go. That should be pretty easy. So we're going to graph f of x is equal to minus 3, and then we're going to answer the question, what is the range of the function f? Now graph the relation, maybe I should make that in bold, x is equal to minus 3, and what is its range? So those are really good problems to do as well. So here we go. I'm going to use the writing space to the right. So f of x is equal to minus 3 is the same thing as y is equal to minus 3. That means every point on the graph, x, y, we have x, y has to be minus 3. X can vary, but y has to be minus 3. So that tells me when x is 0, y has to be minus 3. So I know it goes through this point right here. But when x is 5, y still has to be minus 3. When x is minus 5, y still has to be minus 3. And you've got it. This is a graph. Let me not try to... This is the graph of a horizontal line. And right there we have the graph of a horizontal line. So if you want to take a note over here, the graph of a horizontal line is equivalent to, I'm going to give you both notations. F of x is equal to b, or y is equal to b for some constant b. So what is the range of a function? So let's review the domain and the range of functions. So here's my function. This is f of x is equal to minus 3. So here is how we find the domain. The domain deals with the x values. So imagine you're an ant starting at infinity, minus infinity, and walking toward positive infinity, or basically the left to the right, and you're on the x-axis. Wherever on the x, if at any point on the x-axis you can either look up or look down and find a portion of the graph either above you or below you, then that portion of the graph is in the domain of the function. So no matter where I am, if I look up, if I look down, or if I look up and I look down, I'm going to see some portion of the graph f of x is equal to minus 3, no matter where I am. So that tells me that the domain is minus infinity to infinity. So what about the range? So now consider, instead of the x-axis, that you're an ant on the y-axis. And you're walking up and down, and this time, any point on the y-axis, where you look to the right or to the left and you see a portion of the graph, then that point is in the range of the function. Now, if I'm up here, if I look to the right and I look to the left, I don't see any part of the function, nor down here, nor down here, nor on the x-axis. The only place I see the function is when I'm sitting right on top of it at the point 0, minus 3. So literally, the range is one single point. Remember, we're looking at the y values, and the range is not an interval. It's a single point, and it's minus 3. Okay, so now let's graph the relation. Notice I already changed a word there. Remember, every function is a relation, but not every relation is a function. So B, we have graph x is equal to minus 3. Well, again, for every point on the graph, every point x, y that lies on the graph of this relation, the value of x, the value of x has to be minus 3. The value of y can change. So if the value of y is 0, then minus 1, minus 2, right there is 1 point. That's the x-intercept. If the value of y is 5, there's a point there. If the value of y is minus 5, it doesn't matter. The x value is constant. And in that case, we have the graph is a vertical line. I did not do a very good job of that. Is the vertical line right there. And let's not mess with it any further. So that is the graph of the relation. It's not a function of x is equal to minus 3. So what is its range and what is its domain? Well, using the same test I just did, I want you to think, walking along the x-axis, at what point do you find the graph below or above you? Its domain is a single point at minus 3. Now walking up and down the y-axis and looking right or to the left, what points allow you to see part of the graph? And it's every point. So the range is minus infinity to infinity. Okay. So let's do another one. So the general equation of a line. So let A, B, and C be real numbers. And here's the only caveat. A and B cannot both be 0. A can be 0. If A is 0, B can't be 0. If B is 0, A can't be 0. Then the general equation of a line is AX plus BY is equal to C. So I'm going to give you a concrete example. AX plus BY is equal to C. Minus 3/5 x minus 7y is equal to 5/3. The value of A is equal to minus 3/5. The value of B is equal to minus 7. And the value of C is equal to 5/3. So just for a second, if you had an equation like this, what would you do? I would suggest to transform it into an equation that is equivalent without the fractions. I would say multiply both sides by the LCD of 5 and 3, which is equal to 15. And once you do it, you will get an equivalent equation that does not have fractions. So here we are. Let's go ahead and graph the general equation of this. I'll come off it. Better get a new layer because I never can tell. New canvas, actually. I don't want tons of layers on top of each other. I like Linux because it's fast. The programs I use are just really, really great. They're stable. They're not resource hogs. But I don't want to tempt fate while I'm recording this because I don't want to have to clip together two video clips and render the whole thing if something goes wrong. So here again, we can do exactly the same we did before, and there's a lot of different ways to do this. So if you have your own particular way, let's not use yellow, I need this to be dark. If you have your own particular way, then you go right ahead and do that. But this way always works, and usually it's really easy. That's the reason I'm telling you to do it. Just do a table of values with kitty corner zeros. That's not going to work this time because my constant term c is 0, but I want you to see this. So let's plug in 0 for x. That gives me 4 times 0 minus 5y is equal to 0, which gives me minus 5y is equal to 0. So minus 5 times what number gives me 0? Y has to be equal to 0. So that immediately already tells you if y is 0, x has to be 0. So this is not going to work. It's going to give me the same point if I choose 0 for y. So I'm going to choose another value. And for this value, I'm going to choose 5. Now, you could choose a value for y and solve for x, but I've chosen to choose the value of x to be 5, and then find the value of y. Let's go ahead and plot the one known point. We know it goes through the origin. So now it says let's let x be 5 and solve for y. So 4 times 5 minus 5y is equal to 0. So that's 20 minus 5y is equal to 0. So that gives me minus 5y is equal to minus 20. When I divide both sides by minus 5, that gives me y is equal to 4. And I have the graph of the line goes through the origin, and here is the point. X is 5 here and y is 4 right there, and it goes to the origin, and it's going to look something like that. Just do 1/2 of it. You can just imagine what the other half will look at. Notice this is just a line segment, but we can always only draw line segments because these lines go on forever. So that's the point 5 and 4, and of course this is the point 0, 0, and other points would exist on down here by continuing it on like that. It's not right on, but that's good enough for us. So here is indeed some new notation for you. It's not easy, but you might as well get used to it. This is your introduction to true college. So let x1 and y1 and x2 and y2 be 2 points on a line. And we want them to be 2 distinct points on a line. It won't do us any good if they're the same point. So we're going to find the following. So here's what I tell you. The capital Greek letter that has this triangle little symbol is pronounced delta. And here is a known stumbling block for math. When you see variables or you see Greek letters, for you to conceptually grab it, you have to be able to say a word. So when you see this symbol, you can't think triangle thing. You can't say triangle x. or triangle thing x, you have to say delta x, delta y. Now, you could say triangle x, but then no one knows what the heck you're talking about. That's the Greek letter delta. So when you see this symbol, you need to teach yourself to say delta x. This is delta y. So delta x is x2 minus x1, and delta y is y2 minus y1. And I'm going to give you, for those of you who will be going on to calculus eventually, what we normally do, what delta normally stands for informally. So this is the uppercase. The lowercase delta looks like that. So both of these are delta. The Greek alphabet eventually had uppercase and lowercase symbols, but this is the one we're looking at, and it means change. Conceptually, it's related in change. In this case, delta x is equal to x2 minus x1. That's the change in x values. Delta y is equal to y2 minus y1. That's the change in y values. Now you might say, well, in this particular case, difference might be a better word. And indeed, conceptually it is better, but for the most part, this word or concept right here would apply to delta in the concept of algebra and calculus is usually the better of the two. So delta x is the change in x values, delta y is the change of y values. For you all right now, all you have to do is remember this. So let's take a look. So I'm just going to plot out a really quick informal Cartesian plane. So there's my x and y axis. Now I'm going to draw a line through it. And I'm going to put 2 points on it. I'm going to put a point right here. I use red, that'll stick out. Point right here, a point right here. Now I'm going to choose maybe this color. Now I'm going to come down, straight down to a perpendicular. And I'm going to come straight over here to a perpendicular. Then I'm going to start erasing. Maybe I could leave them there, but I'm not. And this is supposed to be a right triangle. Many times we will denote that by putting the little square here. And let's label some points. This point here will be y2. And this point down here will be x1, y1. And this length right here, this side of the right triangle, is delta y. And this side right here, the bottom leg, is delta x. So what is delta x? It's equal to x2 minus x1. And delta y is y2 minus y1. So we want to know what is the ratio of delta y to delta x. For some of you who are thinking rise over the run, then you're exactly right. That's conceptually what delta y is. That's the rise, and this is the run. By rise, I just mean this segment of the right, this leg of the right triangle. Well, it's equal to y2 minus y1 over x2 minus x1. And what is this? This is defined to be the slope of the line. And we identify slope many times with the letter M. M stands for slope. So let's go back and see what we're doing. So let's find the slope of a line given 2 points. So here's a really important concept that runs throughout math, and it just caused a little bit of a problem in my intermediate algebra class. Mathematical concepts must always be valid, no matter what. That's the nature of mathematics. If the conditions of a definition are hold, or the conditions of a theorem are true, then the statement of the theorem must be true. No exceptions. None. Logically must be true. So here is, I'm gonna connect this together. Don't worry, I've not lost the thought. Here is 2 points, -4 and 8, and 2 and -3. So you get to label them. And you don't have to label them going from left to right. You get to make a choice. And we're going to make the choice both ways. I'm going to label the first point with x1 and y1, and then the second point with x2 and y2. And let's calculate the change in y over the change in x, which is another word for the slope. That's equal to -3 minus 8 over 2 minus -4. Now this is a really important point. I'm going to go over here and write the formula. I'm purposely not writing the minus sign is inherent to the formula. So right here I have -4. It has to bring that minus sign with it. It cannot use the existing minus sign that is inherent in the formula. So -3 minus 8 is -12. 2 minus a -4 is 2 plus 4. It's -12 divided by 6, which is -2. Well, suppose instead of labeling the first one as x1, y1, suppose I labeled it x2, y2, and then I labeled the second one x1, y1. Then our formula for slope, so I'll write slope because that's what this ratio is, the change in y over the change in x, the ratio of the rise to the run. y2, which is 8, minus y1, which is -3, over x2, which is -4, minus x1, which is 2. Well, 8 minus a -3 is +12. 4 minus a -2 is -6. And I get the exact same answer. So here is the conclusion. When a mathematical formula allows human choice, then the result is always the same no matter which choice you make. So you can choose the first point to be x1, y1, and the second point x2, y2, going from left to right, or the other way around, and it does not matter. And the other point here, big, huge note, slope is a real number whenever it exists. So sometimes you'll learn the slope-intercept form. Form y is equal to 5/3 x plus 3. I'm getting a little bit ahead of myself. And you're asked, what is the slope? And you know you can just read it off this particular form. I get the following answer. The slope m is equal to 5/3 x. This is wrong. There is no x. When I put x there, it becomes a variable term, and it's not a real number. Whatever value it is depends upon the value of x. The slope is only 5/3. Okay, so let's go ahead and do number C. I don't want to do all of these. I think it's just a little bit too simple to do every last one of them. If you want to do the second one on your own, it should be minus 11/6. The second one, per my notes, the slope, if you do it, these are also in the book, minus 11/6. So let's do the third one. I have 2 points, 5 minus 3, and minus 2 minus 3. I'm going to show you a different way to do this. You can use the formula, or you can do it by stacking points. Just stack them up on top of each other. Are they minus 2 and minus 3? Yeah, minus 3. And what we're going to do is remember delta y over delta x. And this is the x and the y values. So minus 3. The top, basically I'm subtracting points. Minus 3 minus, this minus 3 has to bring its minus with us. And this is 5 minus, and the minus 2 has to bring its minus with it. So minus 3 minus a minus 3 is minus 3 plus 3, so that's 0. 5 minus a minus 2 is 5 plus 2, which is 7. So the slope is 0. The slope is 0. We would have got the same exact answer if we would have labeled our points as x1, y1, and x2, y2. It's exactly the same. You can do it on your own. It's just if you're in a test and you want to get an answer fast, that's many times the fast way to do it. The only problem is when you're subtracting points, this value here has to go to the numerator, and this value here has to go to the denominator. And if you don't like any of that, just use the formula just like we did up there. However you've done it in the past that works for you, I would suggest do not alter it. So slopes of special lines. This you can just, we've actually derived it already. The slope of a horizontal line is 0. We derived that one. We just did it. The y value in that last example did not change, and its slope is 0. However, the slope of a vertical line is undefined. The reason being is the x values do not change, so when you subtract two x values which are the same, and they're in the denominator, you get division by 0. It might show you or be worth it just to give you a quick example of that. I'm kind of assuming most of this you already know or should have already known if you passed intermediate algebra and you're in this class. Let's just make a point, 1 and 7, and then the next one, our x values aren't the same, 1 and 3. So I'm going to label this x 2, y2, and this one x1, y1. So my slope m is 7 minus 3 over 1 minus 1, which is 4 over 0, and that is undefined. And notice, the thing to notice here are these 2 points never change. So this is the slope, this is the graph of a vertical line that goes through the point, this point right here, 1, 0. So this is the graph of the line x is equal to 1. Why? Because every point on this line, no matter where you draw it, has an x value equal to 1. The y value varies, but the x value is constant. The slope-intercept form of the equation of a line, I've already been talking about it. Y is equal to mx plus b is an equation of the line. It's not the general equation of the line, where the slope is m and the y-intercept is the point 0b. Remember, the y-intercept is a point. We're in 2 dimensions. B is the y value of that point. And I will take off points if you write the y-intercept as just a single number. We're in 2 dimensions now. We're talking about points. Those are our mathematical objects. Now, of course, this requires the slope to exist. M is always a real number. So this equation will not work for vertical lines, because vertical lines do not have vertical lines have slopes that do not exist. Now, I say many times it's easier to find the slope of a line by converting it from the general form to the slope-intercept form. That means solve for y, and that's exactly what we're going to do now. So we're going to find the slope of the line given in example 6. What would be the other way? I could find the x and the y-intercept. That would give me 2 points, and then I could use my delta y over delta x formula, the slope formula, to find it. It's going to be so much easier just to start with, I thought I chose 4x plus 3y is equal to 12. That's what we're given, and what we want is y is equal to mx plus b. So this is what we're given, this is what we want. So what I have to do is I have to solve this for y. So I'm going to move the x term to the other side. It becomes negative, and the 12 stays over. I just moved it a little over to the right. Then I'm going to divide each term by the coefficient on the y term. That's going to give me y is equal to minus 4/3 x plus 12 divided by 3 is 4. So that gives me exactly what I was looking for. Y is equal to mx plus b. My slope m is equal to minus 4/3. Notice there's no x there. And my intercept, 0b, not any intercept, but the y-intercept, is 0 and 4. So that was pretty easy. Graphing a line using the point and the slope. So what are we asked to do here? So graph the line passing through the point minus 1 and 5 and having slope minus 5/3. So there's 2 different ways to do this. And I kind of like to introduce a new concept to students here, because it's helpful for linear algebra. And I'm hoping some of you who are in computer science will take some linear algebra classes. It will certainly give you a leg up over your fellow programmers, because you know linear algebra. Linear algebra is everywhere in computer programming, unless you're transferring data and stuff like that, and then it's still there. So we want a graph. So I'm going to show you one way you can do it, the normal way, maybe the way others have taught you. I'm just going to informally do this right here. So there's my x and y axis. And we have a point, and the point is -1 and 5. So I'm going to pretend that this is -1 and 5. And the slope is -5/3. So what you need to do, let me write this a little bit better, -5/3. So that's equal to minus, where the 5 is in the minus is in the numerator along with the 5, and the 3 is in the denominator, or it's also equal to 5 by itself in the numerator, and the negative is attached to the 3 in the denominator. So remember, informally, this is the rise over the run. So when we're talking about a rise, going up is positive, going down is negative. The run, going to the right, is positive, horizontal now, going to the left is negative. So let's find another point using this. This says go up this says go down 5 units. So there's 1, 2, 3, 4, 5. I'm just pretending that's 5 units. And then go over 3. So that's going to be 1, 2, 3. So it's going to be a point right there. And I can draw my line through it. And we've got it. I'm going to show you that with something a little bit better. I'm not satisfied with that explanation. So here I have GeoGebra up. And what I want to do is I want to find a point at -1, 5. Right there I drew it. So let's scoot in. So our slope was -5/3. So I can come down -5. Here's -1, -2, -3, -4, -5. That lands me on the x-axis, and then I go +3 to the right. 1, 2, 3. And there I put my second point. But what happens if instead of considering -5 and 3, I considered 5 and -3? So let's go back over here. So again, I start with my point, -1 and 5. This time, I have the negative in the denominator. So the 5 is positive. So I'm going to go up 5. So going up 5 lands me to y is equal to 10. And then I go -3 in the left. That lands me right there. And you'll be able to see that when I draw the point, the line through A, that when I scoot out, it also goes to the point we found in B. So it doesn't matter. It doesn't matter. So again, this is an illustration of we get to choose where to put the negative. The validity of a mathematical statement cannot depend on choice. It doesn't matter. You have to choose some way. You have to put the negative in the 5 in the numerator or in the denominator, but not both, of course, and then go about it. However, there's another way, and I like this way better. I'm going to teach you yet one more way. If you're good with this way, you can skip. If you want, if you're curious, you can stay. We're given, we're given a point. We're going to do what's called point addition. So we can add points just like we were subtracting them to get slopes. So here is the formula. Existing point. By existing point, that means a point that lies on the graph, plus adder point, or if you want, slope point, equals new point on the graph. So here I just want to say two things. There's 2 points on the graph. The existing point and the point you get through adding. The adder point may not lie on the graph. As a matter of fact, the only time it will lie on the graph is when the line goes through the origin. So what is all of this? So here we have the existing point. It's -1 and 5. How do I get my adder point? It's the slope point. So this is the delta. This is the delta y and the delta x. So 5 minus 5 is my y and 3 is my x. So my adder point, numerator minus 5, denominator 3. So it's y over x, just remember that. And I'm ready to go. Now I'm just going to add them together. You say, well, how do I add points? But it's super simple. You just vertically add, just like it was a column of numbers. 5 plus a minus 5 gives me a 0. Of course, the result is a new point. And -1 plus 3 is 2. So I get a new point on our graph, which is 2 and 0. Now if I wanted yet another point, I could say, well, here's my new point, and let's add my adder point to it. And I will get yet another different point on the graph. 0 plus minus 5 is minus 5. 2 plus 3 is 5. So 2 and 0, 5 and minus 5. Right there I already have 2 and 0. Let's add 5 and minus 5. And lo and behold, when I move up here, we will find the point D is on the line. So you can do it any way you want. You can just do it visually with a graph, or you can use the adder point method. Okay, so now most of that should have been review. Maybe I should have, you can always fast forward it, so I'm not going to worry about going slow. For some of you, you would prefer it being more slow. For others of you, you can skip, and literally you would probably want to skip to this point right here, because this is going to be the part that is going to be new to you. Well, don't do that on me. The average rate of change. So here we have another formula. So let's read about it. So the average rate of change is the ratio of the change in one value with respect to another value. Hence, the slope of a line represents the average rate of change in y values with respect to x values. So let's go back and let's look at the slope, and let's actually define that. Let's derive it. What is going on here? Scoot. I like this because I really have a huge digital canvas. So my slope, m, is given to y2 minus y1 over x2 minus x1. But anything with the slope can be written as function form. So that's the same as f of x2 minus f of x1 over x2 minus x1, or using their terminology, they used over the interval AB. So in other words, if x2 is equal to A and x3 is equal to B, and let's draw a really quick little graph here. So this is going to be my A, and this is going to be my B, or if you want x1 and x2, and I have a line. Let's draw us a line. Let's put some points right there. That's the corresponding point. I want a different color. It's a corresponding point, x1, f of x1. That's the notation I used. Or a, f of a. Notice all I did is I replaced x1 with the variable a. Here is the other point. That's going to be the point x2, f of x2. Or if you'd rather use the b notation, that's the point b, f of b. And they're talking about the interval, the rate of change over the open interval a over b. Actually, not the open interval. They have it defined for the closed interval a over b. It doesn't make any difference. What happens at the endpoints don't make any difference, but they defined it over the closed interval. I don't really like that. I think it should rather be defined over the open interval, but we're going to go with what the book says. So that's the average rate of change. Let me give you an example of that and how it's going to be used later on. So I'm going to have to draw again a really quick, bigger Cartesian plane, and this time I'm drawing a function. So that's my function. Here's my A, and here's my B. Now notice this is not a straight line, but this is going to be the point A, f of A. So this is f of x right here. That's the graph that I drew right there. And this point right here, here's my B, f of B. So literally, the average rate of change is equivalent to just the slope between those 2 points. Even though the line diverges and does not travel in a straight line, the slope between those 2 points is the average rate of change. So here we have an example. It's an example of what? Oh, Google. So in 2009, Google spent $2,800 million on research and development. In 2013, Google spent $8,000 million on research and development. So their spending increased. Assuming that the change is linear, that means can be described by a straight line, find the average rate of change. So here we can do it in one of two different ways. We're going to do it the easy way. How's that? So literally we have, in this case, our model is a coordinate system where the x-axis is actually time. So this is one where if you want to let x be equal to t, that might actually be something you would do. But we have 2 points on the graph. One of those points, and the y-axis is what? Moolah spent, money spent on R&D. That stands for research and development. And our first point, our time, is a point of 2009 and 2,800 million. And the second point, which I'm just going to graphically represent, is on down the line at the year 2013, and the amount spent there is 8,000 million, or 8 billion. So the average rate of change is just the slope of that line. So let's calculate it up. It's the change in, I'm going to call this x2, y2, call this x1, y1. It's y2 minus y1 over the change in time this time, 2013 minus 2009. And that's really easy to figure. That turns out to be 5,200 million, or 5,200,000,000 over 4, which turns out to be 1,300 million. So that's the average rate of change. In this case, per unit of time. And what is our unit of time? It's a year. Why? How do we know it's a year? Because that's what was given to us, or different years. So here we have a linear model, a linear cost form, a linear cost function. Here's a function. This is our last example of the day. A linear cost function has the form c of x is equal to mx plus b, where x represents the number of items produced, m represents the cost per item, and b represents the fixed cost. The revenue function for selling a product depends on the price per item p and the number of items sold x. It's given by rx is equal to px. So both cx and rx are linear functions. So the profit, what's your profit? Your revenue, how much you get when you sell it, has to be greater than your cost. Or if I subtract the cost from my revenue, I get my profit. So let's actually go ahead and let's use that to solve this applied problem. Yeah, this is the last page, so it won't scroll up anymore. So let's read the problem. Assume that the cost to produce an item is a linear function and all items produced are sold. The fixed cost, what is my fixed cost? We need our function up here. The fixed cost is b. So what I need to find out the specifics for my function What's going on? It's suddenly really slow. I'm just going to get a whole new canvas. So I've got a Cx is equal to mx plus b. And it tells you that the m represents the cost per item and b represents the fixed cost. And then we have our function revenue of x is equal to px. So we have to find out what, these are kind of like function forms, because I don't know what mx and b are, and I don't know what p is, so let's find them out. Let's read it. Cx is going to be equal to, so the fixed cost is b, and it's 1,500. The variable cost per item is 100. So the variable cost for item is m. M represents the cost per item. So m is 100x. So I've got my Cx. And the item sells for $125. So how much is that? The revenue function, Rx, where P stands for the number of items sold and the price for item P. So the item sells for $125. So 125x. So let's compute Px minus Rx. Whoops. Let's compute Px is equal to my revenue minus my cost. Well, it's equal to 100x plus 1,500 minus 125x. So that's equal to exactly not right. I hope you all saw what I did. How did I know I was doing something wrong? Because I quickly realized we'd be losing money. Rx, which is 125x. Here, be careful. Your Cx needs to be put in parentheses because you're subtracting not just the first term but the entire term. So let's get us. So my function p of x is equal to 125x minus 100x minus 1,500, which is equal to 25x minus 1,500. So what they want to know is how many items must be sold for the company to make a profit. So our P of x has to be greater than or equal to 0. So I'm just going to write that down. Our P of x, which is given by this right here, has to be greater than or equal to 0. So I'm solving a linear inequality. Now if you want, you can just, the break-even point is when our profits equal, our cost equals our revenue, and our profit is 0. So if you wanted, you could just solve this as 0 is equal to 25x minus 1,500. And when you find your value of x, you'll know that your value of x must be greater than that. But I don't want to do it that way because they want to know when you're making a profit. And literally, what they want here is when your profit is greater than 0. So let's solve this and we'll be done. So it's a linear equation. I solve it exactly like a regular equation. I'm going to move the $1,500 to the other side. It will change signs. So I'm going to divide both sides by 25. So 1,500 divided by 25 is equal to 60. So x has to be greater than 60. What is x? Our number of items. So as soon as I sell over 60 items, I'm making a profit. Now some of you are really into money and finances, and I remember, you hear these startup companies and you say they've been losing money for 4 years. How can they possibly go on? And this is exactly why they continue to go on. They have, let me give you a graph here. They have already computed that we're going to of course assume that the cost function and the revenue function are linear. And we're going to let this line represent my cost function, and this line here is going to represent my revenue function. So what do we find out? At this point in time right here, at this intercept right here, that's the break-even point. And of course this is going to be time in years, and this is going to be it has to do with earnings. It's money, right? Earnings. So whatever this year is, suppose right now that this represents the year 2020. And for those of you who care to vote, I will remind you now, if you're wanting to vote in this election, of course I won't talk about who I'm voting for, it's completely inappropriate, but we always tell students that they should vote, and I think the registration, it's the 1st of October, maybe I'll send out a thing. So if you're young and you want to vote, this is one to vote for, do it. So here is some year, and what happens in that year? This is our revenue function, and this is our cost function. Our revenue will be greater than our cost, so we break even in the year, say 2023, and from there on out we're actually going to be making money, assuming that this model holds into the future. So you've lost an awful lot of money. You could total up, you can calculate this area and find out how much money you've lost, and then you can literally mathematically project we will recover all of our lost money at the year, say 2030, and then start making gobs more. And that's the basis of mathematics as used in financial models. So I believe that is it for this particular section. And when I see you, or when I do section 2.5, we're going to do more equations of lines and more linear models.